Something unprecedented is happening right now. In September 2025, Earth faces a wave of near misses. Asteroid 2025 FA22 will slip past us at just over twice the distance to the Moon, while 2025 RJ2 surges even closer, less than 300,000 kilometers away. Dozens of smaller objects are being logged at sublunar distances in a single record-shattering week. At the same time, 3I/ATLAS, a chemically bizarre interstellar visitor, accelerates toward Mars on a trajectory unlike anything in the Minor Planet Center's archives. The numbers defy probability. Is this just cosmic coincidence, or are we witnessing a pattern that could rewrite how we defend our planet? The answer may change what it means to be a bystander in the solar system. September 2025 arrives with an unbroken string of alerts. Astronomers at the Minor Planet Center log asteroid 2025 FA22 at just over 2.2 times the distance to the Moon, about 835,000 kilometers. 3 days earlier, 2025, RJ2 slipped by even closer, a mere 0.78 lunar distances, or less than 300,000 kilometers. These aren't isolated events. The week of September 12th to 18th shatters all previous records. At least 28 near-Earth objects pass within the Moon's orbit. That's triple the prior weekly high. Most are small, in the 8 to 25 meter range, the kind that could vanish in the atmosphere or explode like Chelyabinsk. But two, FA22 and RJ2, are large enough to demand global attention, with estimated diameters up to 120 meters. Each detection flashes across the screens of survey teams: Pan-STARRS in Hawaii, Atlas in Chile, the Rubin Observatory in Chile's Atacama Desert, Catalina in Arizona. Data streams in from automated telescopes, processed by software tuned to catch even the faintest, fastest-moving blips. The pace is relentless. New objects are flagged, tracked, and logged, sometimes within hours of discovery. The Rubin Observatory, only months into full operation, contributes a flood of fresh data. Its wide-field camera covers the sky in sweeping arcs, picking up objects that would have slipped by unnoticed just a year before. Statistically, this is supposed to be a once-in-decades event. Population models, corrected for survey bias, peg the odds of seeing more than 25 sublunar NEOs in a single week at less than 1 in 1,500. Even with improved detection, the September surge stands out, a cluster that defies the usual random scatter of asteroid approaches. Some experts speculate about orbital resonances or a hidden breakup event in the asteroid belt, but the majority point to the power of new technology. Detection efficiency now exceeds 90% for objects larger than 20 meters within 1 lunar distance. Blind spots are shrinking, but not gone. Sunward approaches remain a weakness, a lesson seared into memory by the Chelyabinsk airburst 12 years earlier. On social media, the numbers fuel speculation. Charts circulate, showing a spike that looks too sharp to be chance. Orchestrated, some call it. A warning shot, others suggest. In scientific circles, the mood is more measured, but no less alert. Each close pass is logged, analyzed, and archived, feeding into a planetary defense system that is only as strong as its latest detection. For a brief window, the world's attention flickers to the sky, and the question lingers. What if just one of these objects had been aimed a little closer? Imagine FA22 hadn't missed. At 120 meters across, roughly the height of a city block, the asteroid's entry would begin high above the atmosphere, a silent speck hurtling at over 18 kilometers per second. If stony, like most objects of its size, it would compress the air ahead until the pressure shattered it in a violent airburst, much like Chelyabinsk in 2013. But scale matters. Chelyabinsk's shockwave broke windows across 6 cities and sent more than 1,500 people to hospitals, mostly with glass cuts and concussions. FA22 carries more than 20 times the energy. A stony asteroid this size could explode at an altitude of 10 to 20 kilometers, releasing energy equivalent to several megatons of TNT. The shockwave would flatten buildings across dozens of square kilometers. Anyone caught near the blast center would have seconds, if that, to react. Glass would shatter, walls would buckle, and the heat flash could ignite rooftops. The devastation would not be limited to the point of entry. Outlying neighborhoods would feel the blast, with flying debris and collapsing structures multiplying the danger. If FA-22 were made of iron, the story changes. Iron asteroids are denser, more cohesive. Instead of fragmenting, an iron body could punch straight through the atmosphere, striking the ground at nearly full speed. The result? A crater hundreds of meters wide, a fireball visible for miles, and a plume of ejecta lofted into the stratosphere. The local impact would devastate infrastructure, but the environmental ripple could reach far wider, depending on location. Now shift the target to the ocean. Over 2/3 of potential impact sites are water. Here, the energy transfers into a massive steam plume and a series of tsunamis radiating outward. While most of the wave's energy dissipates quickly in deep water, coastal regions within a few hundred kilometers could see walls of water tens of meters high. Ports, cities, and low-lying islands would face catastrophic flooding with little warning. The Chelyabinsk event exposed the blind spot. Objects approaching from the sunward direction, invisible to ground-based telescopes until the last moment. Sergei Karpov, whose dashcam footage became an icon of that morning, still describes the aftermath in terms of noise, glass, and confusion. Years later, he works with disaster response teams, urging cities to rehearse for events that give no warning. His message is simple. The line between a harmless fireball and a city-leveling disaster is thinner than most realize. In the simulations run after each close pass, the numbers are stark. Impact energy, population density, time of day, all variables in a cosmic equation that plays out without malice or intent. The only defense is vigilance, early detection, and the systems that turn warnings into action. Without them, the cost is measured in shattered cities and lives forever changed. SWAN presents a different kind of spectacle. Discovered on September 11, 2025, not by an optical telescope, but by the Solar Wind Anisotropies (SWAN) instrument aboard SOHO, this comet's arrival was announced by a sudden surge in hydrogen emissions. The Lyman Alpha glow, an ultraviolet fingerprint invisible to the naked eye, lit up the data streams before most ground-based observers even knew to look. A handful of backyard observers scanning the Virgo constellation confirmed what the satellites had hinted. SWAN was brightening fast, its tail doubling in length over a single night. This wasn't just a matter of brightness. Spectroscopy revealed a volatile-rich coma, dominated by hydrogen and a smattering of cyanogen and carbon compounds. The outgassing rate spiked as the comet neared perihelion, with hydrogen production outpacing water vapor by a factor that caught even seasoned comet watchers off guard. The reason? SWAN's icy nucleus was fragmenting under solar heating, exposing fresh layers and releasing trapped volatiles in a series of outbursts. Each new crack in the nucleus meant another round of hydrogen flares, visible to instruments tuned for ultraviolet light. Professional observatories scrambled to schedule follow-up observations. The Rubin Observatory, still fine-tuning its survey cadence, devoted emergency time to track the evolving coma. Meanwhile, citizen scientists continued to feed data into the pipeline, timing outbursts, mapping tail morphology, and flagging sudden changes in brightness. Their alerts helped direct high-resolution spectrographs to catch fleeting details. Jets of material arcing away from the core, subtle shifts in the chemical mix, and the telltale signs of structural stress that often precede a breakup event. As September drew on, the risk of fragmentation loomed large. Recent models suggested that SWAN's nucleus, already riddled with fissures, might not survive its closest approach to the Sun. If it broke apart, the resulting debris cloud could produce a spectacular display, visible from both Earth and space. For planetary defense teams, SWAN's volatile behavior served as a reminder: not all threats travel on silent, predictable paths. Sometimes, the warning comes as a sudden burst of hydrogen, and the first line of detection is a global network of amateurs with their eyes and instruments trained on the sky. April 13, 2029 is already circled in red on every planetary defense calendar. On that day, Apophis will pass just 32,000 kilometers from Earth's surface, closer than many communication satellites and visible to the naked eye as it sweeps across the sky. For years, Apophis was the stuff of doomsday headlines, a so-called planet killer first flagged in 2004. But in the years since, the threat of impact has faded, replaced by a rare scientific opportunity, a live rehearsal for planetary defense with the world watching and instruments ready. The close approach is more than a spectacle. Earth's gravity will reach out and tug at Apophis, raising tides not of water, but of rock and dust. Scientists expect to see real changes: surface landslides, regolith shaken loose, maybe even a reshaping of the asteroid's silhouette. These tidal effects have never been measured up close on a body this size. It's a natural experiment that can't be staged in any lab. To capture it, NASA has dispatched OSIRIS-APEX, a spacecraft tasked with rendezvousing with Apophis soon after the flyby. Its mission: document every scar, every rearranged boulder, every trace of Earth's invisible pull. The before and after snapshots will reveal how asteroids respond to close encounters and how small gravitational nudges can change the course of a wandering rock. For Andrea Riley, a systems engineer on the HERA team, the approach carries personal weight. In a diary entry from 2023, she recalls the anxiety of watching Apophis dominate the news as a teenager. That sense of dread, tempered by the promise of new technology, now fuels her work. Apophis is more than a test for scientists and spacecraft. It's a dress rehearsal for humanity's ability to track, model, and, if ever needed, deflect a real threat. Every calculation, every observation, every line of code written for OSIRIS-APEX or ground-based radar is a step toward a future where close calls are met with calm precision, not panic. As Apophis races past, the world gets to watch planetary defense in action, turning a headline once filled with fear into a story of preparedness and discovery. 3I/Atlas, catalogued as C/2025N1, stands out from the first spectrum. On July 1st, Pan-STARRS flagged its hyperbolic path, but it was the chemical fingerprint that sent scientists scrambling for time on the world's largest telescopes. Early VLT X-shooter data, captured as the comet crossed approximately 4.4 astronomical units, revealed a coma dominated not by water vapor, but by carbon dioxide. JWST confirms the numbers in August. Carbon dioxide production at 129 kilograms per second, while water trailed far behind at just 6.6. That's a ratio of nearly 20-to-1, unprecedented for a comet this bright and active. For comparison, most solar system comets flip that ratio, with water outgassing dwarfing carbon dioxide by a wide margin. Here, the usual rules are reversed. The anomalies don't stop at the volatiles. High-resolution spectra from the VLT's UVE's instrument, taken over several nights in July and August, picked up a strong atomic nickel signal, 4.6 grams per second streaming from the coma as of August 21st. But iron, a near-constant companion to nickel in cometary chemistry, was absent, falling below the detection threshold. This nickel without iron pattern is rare even among interstellar visitors. In solar system comets, nickel and iron tend to appear together, liberated by the same heating processes. Theories range from unique formation chemistry to the selective loss of iron during billions of years adrift between stars. Some point to the breakdown of nickel-rich organics, others to cosmic ray weathering, stripping away more volatile iron compounds. No single model fits all the data yet, but the debate is fierce and ongoing. Mid-August brought another surprise. The Mars Reconnaissance Orbiter, scanning ultraviolet wavelengths, caught a sudden flare. An outburst that doubled the comet's brightness in less than 36 hours. Ground-based photometry showed the tail splitting into multiple components, dust streaming in separate directions. These episodic outbursts don't match the usual water-driven jets. Instead, they hint at pockets of carbon dioxide or other volatiles erupting as sunlight penetrates fresh fractures. Rotation studies add to the puzzle. Light curve analysis suggests a slow, possibly tumbling nucleus, spinning on an axis that shifts over time. The period stretches past 22 hours, with only faint changes in brightness, evidence for a nearly spheroidal shape or a complex, non-principal axis rotation. This makes predicting outbursts and tail evolution even harder. Each new dataset adds another layer of intrigue, and with perihelion set for October 29th, the world's spectroscopists are locked in a race to record every detail before the comet disappears behind the Sun. For now, 3 I/Atlas remains a chemical outlier, a slow-spinning messenger from a colder, darker corner of the galaxy.